Okay, so we left off here on section 24.6, which deals with the reactions of monosaccharides. So it says the first reaction that we want to know is that all of these hydroxy groups in our polyhydroxyaldehydes and ketones are monosaccharides. The hydroxy groups of a monosaccharide can be converted into methyl esters to improve their solubility in an organic solvent. Because if you have a sugar like um, glucose, so here's the closed chain, or the closed form here, the pyranose form. This is actually difficult to purify, so difficult to purify, especially using things like chromatography, so using silica like you would on a TLC plate. So what you do is to cover up all these hydroxyls, which are so polar that they stick to silica gel so strongly, they adhere to the surface so strongly. What you do is you do an acetylation where you basically convert all of them into methyl esters using acetic anhydride. So the OAC means you're making a methyl ester. And when you do that, you end up with polyacylation. So you end up with these 5 acetyl groups on here, and now you get something that's easier to purify. I never said it was easy to purify, but easier to purify. And so then you could take that and put it on a column, or you could run a TLC on it much easier. Okay, and so in order to do that, we just use excess of acetic anhydride, and then we use pyridine. So keep in mind that pyridine is like a 6-membered ring that has a nitrogen in it, and it's an aromatic compound. There we go. So acetylation doesn't say that word here, but basically putting all these acetyl groups on the hydroxyls, all these alcohols on our pyranose ring, and we get something that's easier to purify. We can also convert them to ethers, and the same rationale would apply here, that this would be difficult to purify, and of course this would be easier to purify. And this is kind of like a Williamson ether synthesis. Remember the Williamson ether? That was when we took, we had an alcohol, and then we did a deprotonation to make an alkoxide, and we used a strong base. Then we treated it with an alkyl halide, and we did an SN2 like that, and then we ended up with an ether like that. That's Williamson ether synthesis. Well, the thing is, when we did that, we usually used really strong bases. And the problem is, if you use a strong base in the presence of a pyranose, like as is shown here, you get something called epimerization that occurs, and you wouldn't want that to occur. Basically, it's like a type of racemization. It's not racemization, but it's basically you mess with the stereochemical configurations at some of the stereocenters, and I'll talk about that more later on. But what we do is we treat the compound with excess iodomethane, as is shown here. And instead of using a strong base like potassium hydroxide or sodium hydroxide, something like that, we use silver oxide as our base. So this is silver oxide. Remember that silver has only one oxidation state. There's no such thing as silver 1 or silver 2. It's just silver, because silver is always +1. So we have silver oxide, and then we can make this polyether, where you end up with 5 ether groups on here. And again, you end up with something that's a little easier to purify. Well, we've spent a lot of time talking about hemiacetals today, and earlier on in this class, we saw how you could take a hemiacetal, treat it with an alcohol, a catalytic amount of acid, drive the water away, and you could form an acetal. Well, if you look at a pyranose, you can see that this is a hemiacetal, right? Clearly this carbon, and I went over this earlier today in the previous video, that this carbon has an R group attached here, it has a hydrogen here, it has a hydroxyl and an ether here. So this is clearly a hemiacetal. That carbon that I have highlighted in yellow is the only carbon with a hemiacetal on it in the entire molecule. So we can take that carbon, that hemiacetal, and we can treat that with an alcohol like methanol and acid, and we can make an acetal. And the thing is, when you make that acetal, so let's take a look. You have the carbon here, you have an ether here, you have another one here. Yes, you have a hydrogen, and you have an R group over here. So this is an acetal. Well, when you form an acetal on that anomeric carbon, we call that a glycoside. Okay, so that's the special name, is a glycoside. So if you take beta-D-glucopyranose and you treat it with methanol and HCl, you actually get a mixture of two anomers, right? You get the methyl alpha D-glucopyranoside, and you also end up with the beta as well. You see, you have mostly the alpha. Okay, we end up with a mixture, even though we started it with the pure beta. So if we take a look at the mechanism, that's going to help us rationalize as to why we get a mixture. Because the first step is to convert that hydroxyl into a good leaving group. Okay, once we've converted it into a good leaving group, it's going to leave, right? We're going to lose water. Water is the conjugate base of hydronium, which is a strong acid. So water is a good leaving group. Then we end up with this resonance stabilized carbocation, right? So if you take a look, this carbon here is trigonal planar. And so our nucleophile, our methanol, can attack that carbon from either face of the molecule. It could attack from the bottom face, as is shown right here. You see the methanol attacking from the underside of the molecule. And then the methoxy group ends up on the bottom to produce the alpha anomer, or it can attack from the top face of the ring so that your methoxy group ends up on the top and you end up with the beta anomer, the beta glycoside. So this explains why we get a mixture of the alpha and the beta glycoside just by taking a peek at this little mechanism here. Well, as I told you earlier on, I said, well, you don't want to put a monosaccharide like an aldose in a strong base. That's why we used the silver oxide when we wanted to do the methylation. If you put a monosaccharide like an aldose in strongly basic conditions, there's a process called epimerization that occurs at carbon number 2. Look, if we look at the carbons here, we count them. We have carbon number 1, that's our aldehyde carbon, and we have carbon number 2. This is a stereocenter. Well, what happens is when you treat that with a strong base, you end up with something called an ene diol, and you can try to draw the mechanism for that, right? You're going to have the hydroxide, which is going to abstract this proton, and then you could draw the curved arrows to show the formation of the ene diol. But then the ene diol is going to undergo a rearrangement, which is like a tautomerization, but it's going to give you a mixture, right? You're going to tautomerize to have the hydroxyl on either side of carbon 2. So you go from pure D-glucose to a mixture of D-glucose and D-mannose. And we call the relationship between D-glucose and D-mannose, yes, they are diastereomers, right? Because they differ at one stereochemical, one stereocenter, but we call them epimers, which is more specific in that they're diastereomers, but they only differ in the configuration at one chiral center. So we would call them C2 epimers is the way I would describe it. They're carbon 2 epimers, right? They just differ at that one stereocenter. So it's kind of interesting. This is why carbohydrate chemists usually will try to avoid, using strong bases under all circumstances, because you end up with these kind of epimerizations, which are really painful. All right. Well, what are some other reactions we can do? We know, as I told you earlier on, I said if you have the pyranose form of glucose, here we have beta D-glucopyranose, you see, I told you earlier on that you end up with some of the open chain form. Not a lot. Maybe it's only less than 0.01%, but you do have some of the open chain form in a solution. So that means you do have some of this aldehyde present in the solution, right? It's in equilibrium. That was the mutarotation. We saw that the mutarotation between the alpha and the beta form of glucopyranose proceeded through the open chain form. Well, what happens is if you were to subject glucose to sodium borohydride, since you have a little bit of this in your solution, what's it going to do? It's going to reduce it, isn't it? And then you go from an aldose to something called an alditol. So the name of this alditol is specifically D-glucitol. You don't have to have that memorized, but you do have to know what an alditol is. So when you reduce an aldose and you reduce the aldehyde to a primary alcohol, this is called an alditol. Now, if you think about Le Chatelier's principle, right? If there's an equilibrium between the ring, the pyranose form, and the open form, if you start consuming that and converting it into the alditol, what's that going to do here? Is that's going to push the equilibrium in this direction to the open form, and it's going to keep going and going and going until it all gets converted into the alditol. And so we end up with glucitol, which actually has another name, which is desorbitol. It's used as a sugar substitute. It's found in many fruits naturally, but it's also used as a sugar substitute. So you need to know what an alditol is, okay? We reduce an aldose, we reduce that aldehyde to a primary alcohol, and we get an alditol. And I explained where the open chain form comes from for the second time today. And I explained Le Chatelier's principle and how you would keep pushing that forward as you do the reduction. Well, what else can we do here? If we take that open chain form, okay, here again, we're showing the equilibrium between the pyranose form and the open form. If we take that and we treat it with some oxidizing conditions, now it says there's lots of different conditions that can be used, and you could Google this, or you could do a little research on this, and you would see that there are many different ways of affecting the transformation that's shown here. But what we can do is that we can oxidize the aldehyde to a carboxylic acid, and we get not an alditol, but we get what's called an aldonic acid. So you go from the aldehyde to an aldonic acid. And what's cool about these conditions here, which are bromine and water, and it's buffered to a pH around 6. Again, I don't remember exactly how that's done. I think they use calcium carbonate or something. But anyhow, what's cool about this is that this is a way that can be used to distinguish between an aldose and a ketose, because the buffer is going to prevent the ketose from isomerizing, which is kind of cool anyhow. But this is how we make an aldonic acid, is just by taking the open chain form, our aldose, and treating it with bromine and water at a pH of 6, and that causes the oxidation of the aldehyde, but leaves all of these secondary alcohols intact. Okay, and if you're wondering, well, what would happen if we treated it with stronger oxidizing conditions, I will mention that. Okay, so it is coming, don't worry about it. All right, so selective oxidation of the aldose and not the ketose, again, as I told you, is a way to differentiate between the two. And the way that we do that is to use bromine in water at pH equal to 6. So that's what we saw on the last slide. Again, it's only going to oxidize an aldose, will not oxidize a ketose. However, there are many other types of oxidation tests which are really old, and these are ways that chemists use to detect the presence of what's called a reducing sugar. So basically, any pyranose or furanose form of a sugar is going to be considered a reducing sugar. Why? Because it's always going to be in equilibrium with a little bit of the aldose. Okay, even a ketose we saw was in equilibrium. Even when we looked at fructose, we saw that it's a ketose, but it does have some of the aldose in equilibrium. And so we can use tests like the Tollens test, the Fehling's test, and there's one here, I don't know why it's not on here, but the Benedict's test, Benedict's test, and we can use these tests to determine whether we have an aldose or not. So again, it's another way to determine whether you have a pyranose or furanose form of a sugar. It's just a way to distinguish those types of sugars from other sugars that are not reducing sugars. Now, what do I mean by reducing sugar? It's able to reduce something. So for example, in the Tollens test, what you do is you reduce silver ions, you reduce them to silver 0. And sometimes we call this the silver mirror test, And that's not done in that many undergraduate labs because it's so expensive, but you could Google it and find a picture of the silver mirror test. The Fehling's test and the Benedict's test, the Benedict's test, what it does is it reduces copper 2+ ions, which are this nice blue color, to copper 1 ions, which are red in color. And the copper 1 ions are also form a precipitate. And so again, if you're wondering, what the heck are these tests for? If you have a sugar that is able to do the reductions that are shown here, we can either get a silver mirror or a red precipitate, depending on the test. And that way we know that it's a reducing sugar. It is either a pyranose or a furanose, right? Whereas if we have a glycoside, since glycosides are acetals, they don't have any of the pyranose or furanose form where we have the aldehyde in equilibrium, and so they are not reducing sugars, okay, and they do not get oxidized. All right, because again, and I'm kind of harping on the same point over and over, is if the sugar can reduce a metal or a metal ion to a metal or an ion with a lower oxidation state, if it can do the reduction, the sugar is being oxidized at the same time, okay? Sugar is being oxidized, it's causing a reduction, and that's what we call a reducing sugar. Okay, it's not being reduced, it's doing the reduction. All right, there we go. So if we have a glycoside, it is not going to be a reducing sugar. Okay, now, as I promised, I was going to answer the question, what if you treat your aldose with a stronger oxidizing agent like nitric acid? So it says here that if you take your aldose and you treat it with nitric acid, it will oxidize not only the aldehyde, but it will also oxidize the primary alcohol. So here we have a primary alcohol, and it will oxidize that as well. It'll leave all the secondary alcohols intact, but you end up with two carboxylic acids, one on each end, and we call that an alderic acid. Remember, an aldonic acid was when you only had it at the top, but when you oxidize both of them, you get an alderic acid. So again, we don't want to use something like Jones reagent or something like that, because that's going to oxidize everything. And so nitric acid, water, and we cook that up and we can produce an alderic acid. Another really neat reaction of monosaccharides is the Kiliani Fischer synthesis. You remember that earlier on we talked about cyanohydrin formation. If you take an aldehyde or a ketone, you can treat it with HCN and you end up with a cyanohydrin, and that's what these are right here, okay? These are cyanohydrins. Well, of course, the nucleophile, the cyanide, is going to come in and it's going to attack from either face of the molecule. So it can either attack, you know, from here or from here because that carbon is sp3 hybridized. And so you end up with a mixture of stereoisomers. Well, what happens then is you can take that cyanohydrin and you can hydrolyze the carboxylic acid to produce an aldehyde. And the person that discovered this was Fischer, Emil Fischer himself. And so Kiliani, I think he's the one who discovered this part. And then Fischer is the one who came up with this idea down here. And so we call this the Kiliani Fischer synthesis. And what we're doing, in effect, is we're adding a carbon, right? We're adding a carbon overall, okay? And then when we add that carbon from the nitrile, we oxidize it, or sorry, we hydrolyze it rather to the aldehyde. And it's actually not an oxidation, is it? It's a reduction. Yeah, it says it's reduced to the aldehyde, sorry. Anyhow, so we reduce it to the aldehyde rather, and we end up, you know, going from, let's say we started out with a pentose, well then we'd have a hexose. If we had a tetrose, then we'd make a pentose, so on and so forth. So again, it's cool because you lengthen the carbon chain by one, but you end up with a mixture, right? You'd end up with a mixture of stereoisomers. Anyhow, now instead of doing it all, you know, stepwise by first making the cyanohydrin and then doing the reduction, we can do it all in one pot because the nitrile can be converted to the imine, and then that can be hydrolyzed to the aldehyde. And so the way that we do that is this two-step process here. We first treat the aldose with hydrogen cyanide, and then we treat it with hydrogen and palladium with barium sulfate, which is a type of poison catalyst, I guess. And we stir that around in water. And what that does is that, again, it hydrolyzes the imine in situ, okay? So if we go back here, right, what's being shown here, this is the second step, okay? Second step, that you form this imine, which is here. So this is an imine, okay, and then it gets hydrolyzed with the water. So once you form the cyanohydrin, you kind of do the rest in one pot. So there we go. So here's an example. If we were to start with diarabinose, which is an aldopentose, what do? You end up adding one carbon to the chain, and this carbon here is going to be epimerized, right? You're going to end up with the hydroxyl on one side and on the other. And so we would end up with a mixture of D-glucose and D-mannose in this case. And again, you don't have to have these structures memorized. I recommend knowing glucose because it is the most abundant monosaccharide on the planet. But again, mannose, I wouldn't expect you to know that. If you needed the structure for a quiz, I would provide it for you. Okay, you don't have to pull that out of a hat or anything. There we go. So besides lengthening the carbon chain by one, we can also shorten the carbon chain by one, doing what's called the vol degradation. Okay, the vol degradation. I'm probably butchering it. It probably is vol because I think vol is German. But anyhow, the vol degradation. So it's the opposite of the Kiliani Fischer. We, decrease the number of carbons by one. And this is actually a three-step process. The first step is that you take your aldose, you treat it with hydroxylamine to make an oxime or an oxime, whatever you want to call it. Then in the second step, you treat it with acetic anhydride, which essentially does a dehydration, right? You end up losing H2O and you form the nitrile. And then in the third step, you treat it with an alkoxide base, and that does this elimination here to form the aldehyde. So what are you doing is you're decreasing the length of the carbon by one. Now, this whole process, in terms of its utility, like why would you want to do this? I don't know, really. I can't think of a whole lot of uses for this synthesis, except for a long time ago, this was used to characterize aldoses. So when scientists didn't know the structure of an aldose, they could degrade it piece by piece by piece, and then that would enable them to elucidate the structure. So it was really helpful for determining the structures of aldoses in early investigations of carbohydrate chemistry. So the Wohl degradation, or the vol degradation, either way, same thing. Let's take a look here. It says, draw and name the structure of the aldohexose that is epimeric with D-glucose at each of the following positions. So if we draw D-glucose, so we'll draw that out quickly here. So we have D-glucose. And again, this is one of the few sugars that I have memorized. So this is D-glucose. Okay. So if I draw the epimer, let's just copy and paste this. So copy, paste it over here. And we want to draw the epimer at C2. So if I draw the epimer at C2, that means I'm going to erase this and this. I'll put the hydroxyl over here, and I'll put the hydrogen over here. I go to the family of aldoses. I'm not going to go back to that right now because it's quite a few slides back. But this is D-mannose. So we get D-mannose. We do that. And again, you'd have to look at the family of aldoses. If I do the same thing here, so I'll just paste it again. Okay, and I want to draw the epimer at carbon 3. So what am I going to do? I'm going to erase this, and I'm going to put the hydroxyl over here, and this is allose. This is another one that I have memorized because all of the hydroxyls are on the same side. So I get D-allose, and there you go. So epimer, remember an epimer is just this diastereomer that differs in the configuration at one chiral center is all. So we get D-mannose and D-allose in this case. It says here the same product is obtained when D-altrose or D-talose is treated with sodium borohydride in the presence of water. Explain this observation. Let's start by drawing D-altrose. So, and again, you would need the family. So we'll start by drawing D-altrose. I'm not going to take up too much space here. But this is the structure of D-altrose. So 1, 2, 3, 4. It's this. No. Slow down. I feel like the faster I try to draw structures, the more I mess them up. And if we were to treat this with sodium borohydride, okay, in the presence of water, what are we going to do? We're going to reduce the aldehyde. So let's copy the molecule. Okay, let's paste it over here. So then we're going to end up with this compound. So we're just going to reduce that. And then we're going to end up with CH2OH here. Now we're going to draw the structure of D-talose. So D-talose. So that looks like this. Here we go. Okay, in my D-talose, I have a hydroxyl here. Boy, solving these problems is not nearly as bad as having to draw all these carbohydrates. So again, we do the same thing. We treat it with sodium borohydride in water. And what do we get? So I'll just try the copy paste trick here again. So copy this. We'll paste it over here. Come on. Here we go. And we end up with this. Okay. So how do we explain this? Well, it's because we're making an alditol, right? Making an alditol. Okay. And since we got rid of the carbonyl and we have CH2OH on both of the ends, we end up with the same molecule in each case. And that's really the explanation. Give me a thumbs up if you just follow me on the structures here that are produced and we end up with the same molecule. Same molecule. Is everybody with me that these are the same? These are identical? Okay, thanks, Jisoo. Good. All right. Let's take a look. What else did I have planned here? Oh, a few more questions. It says here, of the 8 D-aldohexoses, only 2 of them form optically inactive alditols when treated with sodium borohydride in the presence of water. Let's see here. When we make an alditol, we end up with optically inactive compounds. Oh, I see what they're getting at here. So let's see. If we go back to the family of aldohexoses, so let me go all the way back here and find it. Where's the family of aldohexoses? Here they are, right here. Okay, we can see them a little bit better here. I'll erase some of this spinach that I have. So if we were to reduce any of these, okay, if we were to reduce any of these carbonyls up here to an alcohol, to a primary alcohol, could anybody tell me which ones would make meso compounds? Can anybody give me one that would make a meso compound? Or make a compound that's optically inactive? Right? Remember what meso is? It's when you have a plane of symmetry, right? Like let's say we have cyclohexane like this, and we have 2 stereocenters, but we have a plane of symmetry like this. This is a meso compound. So overall, the compound is achiral. Well, the 2 here that are going to be reduced, one would be allose, right? If we treat this with sodium borohydride in water, we would end up with this compound. So CH2OH, there we go. There we go. And then you can see that when we put in all the hydroxyls, we end up with a meso compound. There's a beautiful plane of symmetry down this guy, right down the middle. I'll draw that line right here, right? There's a axis of rotation here. And what's the other one? Yes, you're absolutely right, Jisoo. There's one more. Could anybody tell me which one? The other one? It's not going to be mannose. No, because that's not going to be a meso compound. There wouldn't be a plane of symmetry. It would be galactose, right? There's no plane, right? If you reduced this, right, to CH2OH, this is not a plane of symmetry. Okay, whereas if you did it with galactose, so sodium borohydride and water, then you'd end up with this compound, which is an alditol. And we have this, this, and this. Put in all our hydrogens. There you go. And now we do have a plane. Good. All right. Good, Courtney. Great. So now we do have that plane of symmetry. Okay, so that's kind of a fun one. That's kind of a neat problem. So this was 24.30. I guess we just solved it on another spot. Okay, let's go back to that question and I'll just pencil it in. Where was it? It was right here. So the answer was what? D-allose was one and D-galactose was the other. D-galactose. All right, and it's because of a plane of symmetry. All right, so yeah, why don't we put it like this? Both give meso compounds. All right, there we go. Okay, determine whether each of the following compounds is a reducing sugar. Remember, is a reducing sugar is a sugar that can be oxidized. Okay, you've got to be able to oxidize it in order for it to be a reducing sugar. What about A? Would that be a reducing sugar? Yes or no? We said that glycosides are not reducing sugars. So would A be a reducing sugar? The answer is no, right? No, because it is a glycoside. Okay, whereas in B, the answer is yes, right? You can draw an open chain form of B where you have an aldehyde. Okay, in order for it to be a reducing sugar, it's got to be able to have an open chain form that has an aldehyde, right? We have going down, so 1, 2, so going up and over, and then up here. Okay, so since it has an aldehyde which can be oxidized, right? This can undergo an oxidation, okay, to give us, it usually gives you a carboxylate instead of a carboxylic acid. But anyhow, let's just imagine it was oxidized to give you a carboxylic acid, okay, like this, okay, like that. Well, as the sugar is being oxidized from its open chain form with the aldehyde functional group, as this is being oxidized, at the same time the metal is being reduced. Either copper 2 would get reduced to copper 1, or maybe in the silver mirror test, the Tollens test, silver would be reduced to silver 0, right? So these are reductions, okay? So that's what a reducing sugar is. It's one that can affect the reduction of a metal. Same thing with the next one. Even though we do have ethers here, it's still a hemiacetal, right? There still is an open chain form because it's a hemiacetal. So the answer for this one is yes, because it's a hemiacetal. And then here it's also a yes, because it is a hemiacetal. Look, the answer to whether it's a reducing sugar is nothing more than, does the anomeric carbon, the one I'm highlighting in yellow, does it have an ether and a hydroxyl? Then yes, it's a reducing sugar, done. Okay? The only things that aren't reducing sugars are going to be glycosides. Okay, another compound that's not a reducing sugar is sucrose, which is table sugar. All right, just give me a sec here. There's something on my iPad. There we go. Okay, let's move on. Draw and name the pair of epimers that are formed when the following aldopentos undergo the Kiliani Fischer chain lengthening process. So what's the Kiliani Fischer? First, we treat it with HCN to make the cyanohydrin. Then we treat it with this type of poison catalyst, so hydrogenation, palladium with barium sulfate. Barium sulfate and water. All right, so what would we end up with? we have how many carbons? We've got 1, 2, 3, 4, 5. So we're going to have 6 carbons. So we're going to end up with an aldohexose. Okay, so let's draw this and this, and then we've got 1, 2, 3, 4. These hydroxyls are still going to be down here, but our new chiral center that's formed is going to have both configurations. So let me draw this first, and then I'll do a copy and paste. So there we go. So we're going to end up with this, which is allose, and then we're going to end up with this, which is ultrose. So we end up with D-allose, and D-altrose. So again, these are C2 epimers. Right. And the next one, we have another pentose. I'm just going to skip this one kind of because I'm running out of space here. But you end up with D-gulose and D-idose. So I'll give you that one to try on your own. So you end up with D-gulose and D-idose. Like that. Okay, let's try one that deals with a vol degradation. My favorite names of I love this last name, vol. Anyhow, so it says when D-glucose undergoes the vol degradation, dang it, followed by Kiliani Fischer chain lengthening, a mixture of 2 epimers is formed. Identify both epimers. I mean, I think you could probably answer this one without drawing out all the chemistry. Well, let's do it. Just because. Let me see here. Did I have D-glucose written somewhere? I did, but it's too big. So let's go back here. Start from scratch. So we'll write out the structure of D-glucose. So here we go. Can you imagine what it would be like if we didn't have the Fischer projection? How long these would take? Okay, there's my D-glucose. So the 3 steps for the vol degradation were hydroxylamine in the first step, followed by acetic anhydride. In the second step, you lose water. Then in the third step, you treat it with an alkoxide base like sodium methoxide. So we end up losing a carbon. Right? We end up losing this carbon completely. And then this one's going to be the new carbonyl. So we would end up with this compound. So make it a little shorter. So we have 1, 2, 3. Then we have a proton here, hydroxyl. There we go. So we end up with this compound. And then we do the Kiliani Fischer. So in the first step, we treat it with HCN. And then just like the last problem, we treat this with hydrogen and palladium, barium sulfate and water. And then we end up with a mixture of epimers. So we end up growing it back out again. And so one of the epimers is going to be D-glucose. And again, we're going to get a mixture of C2 epimers. So we'll put D-glucose over here. So there we go. We're going to have that one. And then we'll paste this back in again. So we're going to have D-glucose. And then the other epimer will be, we just invert that one stereocenter like this. And this is D-mannose. So D-mannose. I can't imagine why you would do this. Why would you start with a beautiful, pure compound and make a mixture of epimers? I don't know, but it's a good exercise when you're learning the content. The vol degradation, again, the vol degradation. It's one of those reactions. I suppose I learned it when I was a student, but I forgot it completely. Like most reactions, you never forget when you're an organic chemist. But the vol degradation is one of those ones that was kind of lost on me until I started teaching chemistry again. It's one of those things I never thought about ever after I did my undergraduate. So that's proof that I don't think it's used a whole lot, but historically it is an important reaction in terms of elucidating the structures of monosaccharides. So I think it does, or it definitely did have its place, and maybe it does have other uses that I'm not aware of. But anyhow, a little bit about the Vol degradation. Again, kind of a cool reaction. So the last two parts that we're interested in is chemistry 3111 students. It's just a few slides. I'm just going to show you quickly. We're going to talk about disaccharides. There's a couple of disaccharides that you need to know. You should know what maltose is. You should know what cellobiose is. You should, of course, know what lactose is because, a good percentage of the population is lactose intolerant. And then you should know what sucrose is. And sucrose, as I told you, is not a reducing sugar. Okay. Then after that, we're going to talk about polysaccharides very briefly. We'll talk about the difference between cellulose, amylose, and amylopectin. And that'll take us to the end because we're going to skip sections 24.9, which deals with amino sugars and glycosides. So if you want to take the time to read those sections, if you're biochemistry minded, it might not be a bad idea to read those, but I won't ask you about 24.9 and 24.10 on your quiz or on the final exam. Okay. And I know